students, so welcome to the solution of day 19 Friday questions on communication systems. The topic was angle modulation, but we have kept one question on amplitude modulation also. I will be discussing the efficiency of the amplitude modulation in the first question. In the second question, I will be explaining the Bessel's function, and very important to know or to understand the spectrum of the frequency modulated signal. In the last, we will be explaining you the Armstrong method to design and to create the frequency modulated signals. Okay, so let's start with the first question, that is efficiency of the amplitude modulation. So let us take the amplitude modulated signal as AC cos omega ct, and let us take the mt, that is a signal, as am cos omega mt, and this will get multiplied by cos omega ct. Okay, now this can be written as AC 1 plus mu cos omega mt cos omega ct, where mu is equals to am upon AC, and we know that we need mu should be less than 1. Now the power of the am signal, the power of this signal, okay, will be equals to AC power of the signal will be equals to the power of this signal. Just I am writing the signal cos AC cos omega ct plus AC into mu cos omega mt cos omega ct. This can be written as AC cos omega ct plus mu AC by 2 cos omega m plus omega c into t plus mu AC by 2 cos omega c minus omega m into t. Okay, so this is the signal. Now we can see that this is very important, that this is the carrier and this is the upper sideband and this is the lower sideband. Okay, so this is the upper sideband and this is the lower sideband. This is the carrier. Okay, now if I want to find the power, we can see that the carrier power is AC square by 2. The power of this signal is mu square AC square by 4 into 1 by 2. Thus the power of this signal will be mu square AC square by 4 into 1 by 2. Now this is the carrier power and this is the power in the sideband. So this can be written as AC square by 2 plus mu square AC square by 4. Okay, so this is the power of the AM signal. Now the power of the AM, the efficiency of the AM signal is equals to the power in the sideband divided by the total power. So the power in the sideband is mu square AC square by 4 upon AC square by 2 plus mu square AC square by 4. Okay, so this comes out to be, we will cancel this AC square by 4, so we will get mu square upon 2 plus mu square is the efficiency, and if we multiply it by 100 we will get the answer in percentage. Okay, so this is the solution to the problem. This is the efficiency. Okay, now one more very important point is that, so here in this case we have taken the MT signal as a sinusoidal signal. Suppose we have just a generalized problem. Suppose we have MT any signal and it is getting modulated. Okay, so the AM signal will be, now the AM signal will be AC cos omega ct plus MT cos omega ct. The only requirement is that the magnitude of, that is the AC should be greater than the maximum value of the maximum or minimum value of the MT. That is the requirement of the AM signal. Okay, and also this is the carrier and this is the sideband. Okay, so if in any general question we can solve it like this, that the carrier power will be AC square by 2 and the sideband power will be the power of MT divided by 2, or that is power of MT signal divided by 2 is the sideband power. Okay, so the efficiency in the general case will be the power of the MT signal divided by 2, power of the MT signal divided by 2 plus the carrier power, that is power of the M divided by power of the signal plus AC square. Okay, so this is a general equation for the general case, efficiency equation for the general case. Okay, now let us solve the other parts of the question. The other parts of the question is we have to find the efficiency for mu equal to 0.5. Okay, that is 50% modulation. So part A, here mu is equals to 0.5. So efficiency is equals to mu square upon 2 plus mu square, and this will come out to be 0.5 square upon 2 plus 0.5 square into 100 to get the answer in percentage. So we'll get 11.1% as the answer. Second is, as we can see here, that as the value of mu will increase, the efficiency will increase, because as the value of mu increases, the content in the sideband increases. Okay, so sideband power increases. So efficiency maxima will be at where mu is equals to 1, that is modulation index is equals to 1. So this will come out to be 33.33%. Okay. Okay. Now let's look at this. It is given that the carrier is angle modulated by the sum of two sinusoids. So these are the two sinusoids. Okay. So this is angle modulation. Okay. Now we have to find out the spectrum of the signal. Okay. Now for spectrum of the signal, we will first of all look at the angle modulation of the single sinusoid. Okay, single sinusoid. So let us assume that a new signal XST is equals to A cos omega CT plus beta sine omega MT. Okay, so this can be written as real part of A times real part of e to power j omega CT plus beta sine omega MT. Okay, so there's a bracket here. Okay, so we can write XST is equals to A times real part of e to power j omega CT plus beta sine omega MT. Okay, so this is the expression of XST. Now as we know that let us look at e to power j beta sine omega MT. Now since this is a periodic function beta sine omega MT, so this whole signal will also be a periodic signal. Okay, so this will be periodic with period 2 pi by omega m. Okay, the period of this signal, the period of this whole signal will be same as the period of this individual signal. Okay, that is 2 pi by omega m. So since it is periodic, it can be written in the Fourier series form. So that is equals to, so this can be written as, let us say Cn is the exponential Fourier series coefficient, that is Cn e to power plus j n omega m t, n is going from minus infinity to infinity. Okay, so we know the formula of Cn is equals to 1 upon time period, that is 2 pi by omega m, integration over one time period, that is pi by omega m to pi by omega m, the signal e to power j beta sine of omega mt e to power minus j n omega t dt. Okay, so this is the formula. So this is equals to, let us say omega mt is equals to x. Okay, so dt is equals to dx upon omega m, or omega m into dt is equals to dx. Okay, now since this omega m will go in the numerator, so we'll get omega m dt in the numerator. So Cn can be written as minus pi to pi 1 upon 2 pi e to power j beta sine x minus nx dx. Okay, and this is what the Bessel's function is. Okay, so Bessel's function j n beta is equal to 1 upon 2 pi integration minus pi to pi e to power j beta sin x minus nx dx. This is very important because GATE has not asked any question related to Bessel's function till now. They can ask you, okay, the value of the Bessel's function is given to us and we just have to recall that what is the equation of the Bessel's function. Okay, so we can say that Cn is equals to Jn beta. Okay, so we can write e to power j beta sine omega mt is equal to summation n equals to minus infinity to infinity j n beta e to power plus j n omega m t. Okay, now we can easily write this expression. Okay, so we know that xst was a times real part of e to power j omega ct plus beta sine omega mt. Okay, so this can be written as a times real part of e to power j omega ct, and e to power j beta sine omega mt will be written like this: n equals to minus infinity to infinity j n beta okay, so this will come out to be a times real part of n equals to minus infinity to infinity j n beta n omega m plus omega c into t. So this will give us summation j n beta into a n equals to minus infinity to infinity cos of n omega m plus omega c into t. So this is the expression, and this is the expression for the single sinusoid or single tone frequency modulation. Okay, so this is the expression, and here we can easily see that if the signal through which for frequency modulation was done was of frequency omega m and the carrier was of frequency omega c, so the frequency modulated or the angle modulated signal xst has frequencies of omega c plus minus n omega m, where n is going from minus infinity to infinity. Okay, so this is important. Now let us see what is given to us in the question. Okay, so this is given to us that we have to find the expression of this signal. I think I have to add more pages here. Okay, so xct is given to us a cos omega ct plus beta 1. Let me just see what is the equation. So beta 1 sine omega 1t, beta 2 sine omega 2. So this can be written as a times real part of e to power j omega ct, e to power beta 1 omega, sorry, beta 1 sine omega 1t, e to power j beta 2 sine omega 2t. So from the above discussion, we can see that e to power j beta 1 sine omega 1t will be written as summation jn beta 1 n equals to minus infinity to infinity e to power j n omega 1t e to power j beta 2 sine omega 2t will be written as minus infinity to infinity j n beta 2 e to power j n omega 2t. Okay, so this can be then, now we can easily write xct a times real part of e to power j omega ct. So we have to change the variables. Okay, this is m. Okay, here also it is m. Okay, so n equals to minus infinity to infinity j n beta 1 e to power j omega 1 n t multiplied by m equals to minus infinity to infinity j m beta 2 e to power j omega 2 mt, and this is the, so this can be written as a times real part of m equals to minus infinity to infinity j m beta 2 summation n equals to minus infinity to infinity j n beta 1, and this will be a times e to power j omega ct plus omega 1 nt plus omega 2 mt. Okay, now since it is a real part, so we'll get cos, so a times summation m equals to minus infinity n equals to minus infinity to infinity infinity j n beta 1 j m beta 2, and here we'll get cos terms. So cos omega ct plus n omega 1 plus m omega 2 into t. Okay, so this is the expression of xct. So we can see that the frequency modulated signal has terms at frequencies omega c plus n omega 1 plus m omega 2, where n and m both are going from minus infinity to infinity. Okay, so like this we can easily get the solution or the spectrum of the frequency modulated signal. Okay, single tone and the double tone frequencies, as we have seen in the explanation and the solution. Okay, so this kind of question gate has not asked till now, but you can expect this question. Okay, now let us solve this question. Okay, so I will explain you what is the frequency multiplier and what is this mixer is doing. So this is a mixer. Okay, okay, so frequency multiplier. Okay, so let us look at these two boxes. So it is a frequency multiplier and a mixer. Okay, so frequency multiplier, suppose the input is cos of omega 1t, and there is a frequency multiplier which has multiplication factor of n1. So we will get the output that is cos of n1 into omega 1t. Okay, simple. The whole term of the frequency get multiplied by n1. Now if you look at this, what is this frequency multiplier is? So frequency multiplier is simply a nonlinear device. Okay, a nonlinear device. Suppose we have cos of omega 1t and we want cos of 2 omega 1t. Okay, so what we will do? We will pass this signal through a nonlinear device which has the expression that output is equals to input square. Okay, so we can see that the output we will get cos square omega 1t, that is equals to 1 plus cos 2 omega 1t divided by 2. So now this system will be followed by an amplifier which has a gain of 2 and a band pass filter which has a center frequency that is 2 omega 1. Okay, so now then we will get this result. So whenever in any interview or anyone asks you what is a frequency multiplier, so here we can easily see that the frequency multiplier is simply a non-linear device followed by an amplifier, or we do not need an amplifier, we just need a band pass filter which has a pass band gain of 2. Okay, similarly in another case also, if we want cos of 3 omega 1t, that is we need a multiplication factor of 3, so we can have a nonlinear device which produces output equals to input cube. Okay, and it should be followed by a band pass filter which has a center frequency of 3 omega 1. Okay, so similarly we can exactly say that a frequency multiplier is simply a nonlinear device followed by a band pass filter. Okay, now let us look at what is a mixer. Okay, so let me explain you mixer here. So mixer is, so this is inside a mixer. Inside a mixer we have a multiplier followed by a band pass filter. So this is a mixer. Suppose we have a two frequencies, cos of omega 1t and another frequency of cos of omega 2t, and both are given as an input to the mixer. Then this is a mixer, right? So mixer, first of all, mixer has a multiplier. So we can see that here we will get cos of omega 1t multiplied by cos of omega 2t. So here we have two frequencies. One signal is of frequency omega 1 plus omega 2. Other one is of frequency omega 2 minus omega 1. Okay, we have two frequencies. Okay, now the output of the mixer can be omega 1 plus omega 2, a signal with omega 1 plus omega 2 frequency, or it can be omega 1 minus omega 2 frequency signal. Okay, it will depend on the band pass filter. Okay, it will depend on the band pass filter what is the output. Okay, so we can say that the output will be cos of omega 1 plus omega 2 into t, or cos of omega 2 minus omega 1 into t. It will depend on the band pass filter. Okay, now since the mixer and frequency multiplier are clear, we can easily solve this question. Let us first of all paste the question figure. Okay, so this is the indirect method that is called the Armstrong method of frequency modulation. Okay, so this is the signal MT, and we are doing the NBFM, that is narrowband frequency modulation of MT, and it is given that after narrowband frequency modulation, the F1, that is the format of narrowband frequency modulation, is so for simplicity let us assume that MT is equals to AM cos omega MT. Okay, it is just for sake of simplicity. So NBFM, the expression will be AC cos. So let me first of all write, since it is FM, so since it is FM signal, so ft, that is the frequency, the instantaneous frequency of the signal, carrier signal, will be fc plus kf into mt, that is fc plus kf into am cos of omega mt. Okay, so this is the frequency with respect to time of the carrier. Okay, so the modulated signal will be AC cos theta t, where theta t is 2 pi times integration of ft. Okay, so we can say that the modulated signal will be AC cos 2 pi fct plus 2 pi into kf into am, integration of the cos. So integration of cos is sine omega mt, and we'll get omega m in the denominator also. Okay, so let us say that this term is beta. Okay, so this is a constant term. So this is AC cos 2 pi fct plus beta sine omega m t. Okay, or even if we do not write beta, then also it will work. Okay, then also it will work, so there is no need of it. Okay. So we can say that this is the expression of the NBFM. The only requirement of the NBFM is that this term should be very small, or we can say that the frequency deviation should be very small. Okay, so since at this point A, the frequency should be delta f1, and delta f1 should be the frequency deviation. So we can say that the modulated signal will be AC cos 2 pi f1t plus 2 pi into kf am upon omega m sine omega mt. Okay, and we can see that the frequency deviation is kf into am. So delta f1 is equals to kf into am. Okay, so this is the NBFM. Okay, narrowband frequency modulation. Now when this signal is transferred from a frequency multiplier, we know that frequency multiplier simply multiplies this whole term by n1. So we'll get AC cos 2 pi n1 f1t plus 2 pi n1 kf am upon omega m sine omega mt. Okay, so frequency multiplier, we can easily see that the frequency multiplier multiplies the carrier frequency also and multiplies the delta f also. So the new carrier frequency is n1 into f1, and delta f2 is equals to n1 into, so this was delta f1. Okay, so we have f2 is equals to f2 is equals to n1 into f1, that is 64 into 200 kilohertz, that will come out to be 12.8 megahertz. Okay, and delta f2 is equals to n1 into delta f1, and we know that delta f1 was 25, so this will give us 25 into n1 is 64, and this will come out to be 25 into 64, that will come out to be 1600 hertz. Okay, so we can easily see that the concept is multiplier multiplier multiplies the carrier frequency and delta f both. Okay, so carrier multiplier will change both the carrier frequency and delta f. Now this signal, that is this signal, as we can see from the figure, is just passed through a mixer, and mixer has this oscillator which has a frequency of 10.8 megahertz. Okay, so this signal is applied to a mixer. So to a mixer, we have two signals. We know that one signal is of frequency FLO. So we can write this as A times cos of 2 pi FLO into T. And another signal is a frequency modulated signal, that is this signal. Okay, so I will write it as AC cos of 2 pi F2T plus 2 pi N1 into kf am upon omega m sine of omega mt. Okay, so this is another signal. Now when we will multiply, then we can assume that this is theta. Okay, this is a theta t. So this can be written as, I'm just multiplying two signals. One signal is AC cos of 2 pi f2t plus theta t. Another signal is A cos 2 pi FLOT, and at the output we will get the product of these two, and mixer is, we will have a band pass filter at the output, and then you will get the output. Now if we observe this here signal here, so the signal here will be, let me just it will put AC into A, and it will be cos of 2 pi f2 plus FLO into T plus theta t divided by 2 plus cos of 2 pi f2 minus FLO plus theta t. Okay, so we will get two signals. We have this or this. Now if the band pass filter is having the cutoff frequency, has the cutoff frequency of f2 plus FLO, then the output will be some constant AC into A divided by 2 cos of 2 pi FLO plus F2 plus theta t. And if the cutoff frequency of the band pass filter is F2 minus FLO, then the output will be AC into A divided by 2 cos of 2 pi F2 minus FLO plus theta t. The important point here is that the output will have change in the carrier frequency only. Okay, but the theta t will remain same as that of the input to the mixer. Okay, so the input to the mixer was having this as theta t term, so the output is also having a frequency modulated signal having the same theta t, only the change in the carrier frequency. Okay, so the important point is that the mixer changes the carrier frequency only, and the carrier frequency will change to F2 plus minus FLO, and the delta F will remain same. Okay, so let us say that So as we know that F2 was 12.8 megahertz, FLO is 10.8 megahertz. So the output to the mixer will have the carrier frequency, that is the addition of these two, that is 23.6 megahertz, or the subtraction, that is 2 megahertz, but the delta F will remain same, that is 2. What was the delta F at the input? Was 1600 hertz, so it will remain the same, 1600 hertz. So the mixer changes only the carrier frequency. So let us say that we take the higher one as the carrier frequency, 23.6 megahertz. So the output to the mixer is AC into A divided by 2 cos of 2 pi FC plus FLO into T plus 2 pi KF AM into N1 upon omega M sine of omega M sine of omega mt. Okay, so delta F is same, and only the carrier frequency is changing. Now this is applied to a frequency multiplier with multiplication factor, that is N2 is equals to 48. Okay, so the carrier frequency FC plus FLO will change to FC plus FLO into 48. That will come out to be 48 into 23.6, that is 1132.4, 0.8 megahertz, and delta F will also get multiplied by 48. So delta F was 1600 multiplied by 48, and this will come out to be 76.8 kilohertz. This whole question can be done in a much simpler manner, because now I have explained you that what is a frequency multiplier and what is a frequency mixer. So frequency multiplier changes delta F and the carrier frequency. The mixer changes only the carrier frequency. So here the carrier frequency F1 and delta F1 is the frequency deviation or the change. Now frequency multiplier will multiply it with N1. So here we will get a carrier of frequency N1 into F1, and the frequency deviation will be N1 into delta F1. Simple. Now this frequency mixer will only change the carrier frequency. It will change the carrier frequency N1 into F1 plus minus FLO, but the deviation will remain the same, that is N1 into delta F1. Okay, at the output here frequency multiplier changes both, so it will give us N2 into N1 F1 plus minus FLO, and N2 N1 into delta F is the deviation. Delta F1 is a deviation. Okay, so this is the manner in which we can easily solve such questions in the very less time. Okay, the only requirement is you should know what is frequency multiplier and what it changes, what is the frequency mixer and how it changes the signal frequency. Okay, so thank you students.